All right, once again, Scott MacKenzie, News in Brews, right here, MD&M West, broadcasting on the floor. As you can see, if I turn around, you can see the floor and all the buzz that's taking place. We've got Todd. Todd with Lumenous Device. No. Device Technologies. Did I get it?
You got it. You got it.
All right. For the listeners, for the individuals that are sort of hanging out and they're just saying, I want to know, outside the fact that I'm looking up to you. Oh, gosh. But give us a little background on who Todd is.
Todd. I do hard things. I have 5 kids, and one was a bonus 8 years after the 4th. And we dig deep in technology and bust out new developments. I want to say developments, discoveries and advancements all the time.
All right. Can I take the name of your company, Lumenous Device Technologies? Can I just compress it to Lumenous?
Please do.
Thank you, because I'm going to stumble as sure as I don't have hair. All right. So for everybody out there, tell us a little bit about what Lumenous does.
First, I got to tell you what luminous means, because you jumped on the name so purposefully. Lumen is a Latin word for light, or a measure of light power, right? It also has the meaning of passageway. Our company, passageway, yeah. So our company uses laser light to produce components to treat passageways in the body.
Okay, so that's what your organization, your company does, passageways. So you're in the medical space.
Right, exactly.
I got to go down this road. So how long have you been in business?
I joined the company 30 years ago this year.
How old is the company?
I think it had been in existence a couple years before that, 32 years, something like that, yeah.
Okay, so you've been there since the beginning. Now, so you're dealing with passageways. Got it. Why is that important? Take us through an application, please, so that everybody understands this. I have some understanding of passageways, but I guarantee you it's not your understanding. So take us through.
So a classic passageway, and the first one we got involved in, was the coronary artery. It's the one that if it's blocked, you have a heart attack. And in those days, the standard way of treating that was open heart, stopped heart. So you're on a bypass machine for 40, 45 minutes. Surgery, taking a graft from your leg or a mammary artery and doing basically a jumper cable from the aorta to the clean side of the vessel that's blocked. And the solution that was being proposed at that time, early stage, nobody knew this word back then, but I'll introduce another word, stent. It was basically a little scaffold, circular tubular scaffold that could be expanded because it had slots cut in it, so it wasn't a rigid tube anymore. It could be expanded radially. So you could go in on a balloon catheter, which was at that point like a 20-year-old technology, and expand the balloon, collapse the balloon, leave the stent in place, and leave that passageway open without a big surgery. So that's how it all started for us. Our president.
You did stents?
Yeah, we made coronary stents. It was the first product. And at that time, they were being made with wire EDM, which is basically, consider it like a hot wire. I won't get into the details of it. And you basically erode the metal atom by atom. It's really slow. So this little 15 millimeter long stent would take about 45 minutes to cut with an EDM. And the worst part is it left micro cracks.
Okay, hold it. EDM.
Yeah, electrode discharge machining.
Okay, and then the last word?
That process would leave micro cracks in the stent, which then make it susceptible to fracture later, right? And so our boss saw it, didn't know this history, but saw it at an event, and he asked how they made it, and they didn't know, so they ran around, found somebody who knew, and informed him it was wire EDM, and he asked if they'd ever considered laser, and they said, yeah, we tried that. That doesn't work. About a year and a half later, we delivered equipment to him with a laser. It was effective, no micro cracks, and instead of 45 minutes, it was taking 12 minutes.
To produce?
Yeah.
To produce the stent itself?
Right, to do the laser cutting aspect of it. There's finishing afterwards, and then by the time the last time we cut that pattern, we were hot rodding it to see how fast we could go. We got it down to 90 seconds. So from 45 minutes to 90 seconds.
With no defects? Or I mean, in the sense like the micro cracks?
Right. Gone. Yeah.
Why? Why is the technology in such a way that allows it to make those fine cuts with minimal?
Right. Yeah. The laser process is fast, hot, a hot edge. It melts that material, and a cyst gas blows it out of the way, and it leaves a slightly heat affected zone on the edge where the cut went. But then you do some post processing, especially electropolishing, and clean that up and round the edges and leave a biocompatible surface.
See, this is just all I'm looking at, and what is in my mind is the fact that I've got this little teeny thing, and you're talking about as if it's a big piece of product that you can sit there and buff and hone and clean up and all that stuff. But I know it's just tiny. How?
So there's chemical processes, there's abrasive processes, and there's electrochemical processes. And so the final one is kind of the most eye-popping. It's electropolishing. And if you've heard of electroplating, it's, crudely speaking, you take that, reverse the polarity, and you change a bunch of other stuff. But then it'll work. It'll take material off, and you can allow it to preferentially take it off the corners. Control that. We actually have a unique capability of controlling that corner rounding independent of the leveling, smoothing, and dimensional reduction.
Okay, so I've been very fortunate to see other laser cutting processes from the big applications, which is pretty cool. I got to tell you, it's pretty cool. But yours are pretty tiny and very precise. How long have you been, and there's a method to my question here. How long have you been dealing in the world of lasers?
When I started 30 years ago, that's the first time I played with a laser. Yeah, and every micron counts. To your point, every micron.
So fast forward, we're here today, 30 years later. How has it changed? How has the laser technology changed?
Wow, it's like a whole universe of a question there. Wow. Yeah. The kind of laser we used then, we don't use for this anymore. That was awesome, solid state. Awesome. I can't even get into the. It was a beautiful beast of a laser, right? And you have to align it, keep it aligned. You have to manage the temperature. I mean, I'd love to get into that deep because it's a beautiful thing, but we don't use them anymore. We have fiber lasers now, primarily, that generate. They don't have a resonator cavity for the light to bounce back and forth in and get more and more amplification and finally exit out the window. The mirror, it's a partial mirror, so it lets some out and goes down to the workpiece. Now it's just all produced in the generator and the fiber itself, and it's really stable. You don't have to manage its alignment all the time. It's really come a long way. And the length of the pulse that we can use today, we used to use like a microsecond pulse, a millionth of a second. Now we're, nanosecond, picosecond, femtosecond. Not 1 femtosecond, but say 200-300 femtoseconds.
Amazing. Absolutely amazing. And all I remember is that what you have a situation where you have this massive amount of support equipment for that laser to be able to do the laser stuff, right? Which is just absolutely fantastic. And now it's gone, in a sense. Where do you see it going?
We see more continued development in lasers, not like the sea change that we saw with the Pico and Femto, but today you can buy a fiber laser that does that Pico and Femto work, which was, even that was unheard of 5 years ago, 10 years ago. I'm on the edge of my seat to see what they're going to bring us next.
Dead sexy. What makes Lumenous, just the company itself? What's the heart and soul of Lumenous?
Right. I told you the history, and that history generated in us the characteristic of relentless. So we relentlessly pursue discovery. We relentlessly pursue advancement and move what can be done forward into what is being done. As an example, and you asked earlier, like what's coming next. A lot of catheter systems are necessary to get all over the body in all these places we talked about. Talked about how we're in the bones and we're in the eyes, the hardest and softest tissues, but a lot of these passageways. And these catheter systems confront, barriers like friction, within themselves and with the lumens that they're in. And PTFE is one of the, it's the slickest substance we know for solid materials, but it has its downsides. And we have developed a laser cut tube solution for catheter shafts, like the backbone of the shaft that gives it its stiffness and its bending properties. That has to be covered with something. It's not bare metal. And instead of PTFE, we've developed with a partner a laser cut tube coated with a material that's as lubricious, as slippery as PTFE. But the kick is this. This material slides, slippery, but it sticks to the catheter shaft. Now, PTFE won't stick to the catheter shaft. You have to kind of force it and fight it to get it to stay. And that forces your design into uncomfortable directions. So you're not really designing for the anatomy with PTFE. Sometimes you're designing against the PTFE to make the whole thing stay together and not delaminate, fall apart, and leave particulate in the body. Right. So the new one, EverGlide Plus and EverGlide, that series of materials, in conjunction with a carefully designed laser cut shaft, it opens up the body to more exploration for therapy. More therapies, better outcomes.
Anything else? Is that it? Does that cover? Because
That's
that's
just the beginning.
awesome.
That's just the beginning.
It's awesome. Todd, right there.